What do you do when one object shows not one odd feature, not two, but 22 separate anomalies, each recorded in scientific papers, each backed by observations, and each refusing to fit the normal picture of a natural interstellar comet? That is the question hanging over 3I Atlas right now. This morning, a Harvard astrophysicist with more than 900 peer-reviewed publications released an article with a striking title, 3I Atlas is fading away, leaving us to think about its 22 mysterious anomalies. And the timing matters. In just 3 days, 3I Atlas passes Jupiter. After that, it heads outward towards Saturn, Uranus, Neptune, and then into interstellar space, never to be seen again. Whatever this object truly is, whether it is a natural comet, an ancient remnant from another era of the galaxy, or something even harder to explain, our chance to study it is running out. So before it disappears, we need to walk through the evidence carefully, one anomaly at a time, because in this story, the numbers matter more than the hype. Before we begin the list, one idea has to be clear. In science, anomalies are not shocking by themselves. Every object can have quirks. Every data set can contain something unexpected. One anomaly means almost nothing. Two could still be a coincidence. The real question is when a growing pile of coincidences stops looking accidental. Avi Loeb's approach is simple. You estimate the probability of each geometric anomaly happening by chance, then multiply those probabilities together. If the combined result falls below 1 in a million, you no longer have something easy to dismiss. That is the framework here. And the 22 anomalies fall into 4 broad groups: mass budget, geometry, possible technosignatures, and composition. The first anomaly is the mass budget discrepancy. Hubble measured the nucleus of 3I Atlas at about 2.6 kilometers in diameter, based on observations taken between December 2025 and January 2026 after removing the coma. Then isotope measurements published on March 6 suggested the object formed in a metal-poor environment roughly 10 to 12 billion years ago. That points to a very old stellar population with low metallicity. The problem is that protoplanetary disks around such stars are not expected to contain enough solid material to produce enough large interstellar objects for one like this to be detected so easily. In plain language, if 3I Atlas really came from that kind of ancient metal-poor system, there should not be enough similar objects out there to explain why we found one. This is not assigned a neat probability, but it sets the stage for everything that follows. The second anomaly is its trajectory alignment. Interstellar objects are expected to arrive on random paths, and 3I Atlas did come in on a retrograde orbit, which is normal enough. But it also arrived within 5 degrees of the ecliptic plane, the flat plane where the planets orbit the Sun. That is not what you would expect from a random interstellar visitor. The Milky Way's disk is tilted by about 60 degrees relative to our ecliptic, so there is no obvious reason for a random incoming object to line up this closely. The probability of that happening by chance is about 0.2%, or 1 in 500. That gives us our first concrete geometric odds. The third anomaly is the timing. 3I Atlas did not just enter near the ecliptic, it came in on a path that created unusually interesting close approaches, including about 29 million kilometers from Mars and 54 million kilometers from Jupiter. At the same time, when it reached perihelion on the 29th of October 2025, Earth was on the opposite side of the Sun, meaning the object became unobservable during the most scientifically important stage of its passage. Its peak activity was hidden behind weeks of solar conjunction. That alone does not prove anything, but it is part of a pattern. Then comes anomaly 4, and this is where the geometry gets even stranger. On the 16th of March 2026, 3I, Atlas is expected to pass Jupiter at 53.6 million kilometers. Jupiter's hill radius, the region where its gravity dominates over the Sun's for nearby objects, is 53.5 million kilometers. The difference is only about 100,000 kilometers, a match within 0.2%. Loeb has pointed out that an object released from 3I, Atlas, with the right velocity, could become gravitationally bound to Jupiter. That is why he has openly suggested that missions like Juno, JUICE, and Europa Clipper should examine their data after the flyby for any new small satellites. And that takes us directly into the next anomaly, where the object stops behaving like a normal comet and starts raising even harder questions. The fifth anomaly is the strangest visual feature of all, the sunward jet. Normal comets grow tails that point away from the sun because solar radiation and the solar wind push gas and dust outward. But 3I, Atlas showed an anti-tail pointing toward the Sunday. Anti-tails can happen in ordinary comets, but usually they are only perspective effects created when Earth crosses the comet's orbital plane and looks through the dust left behind in its path. That is not what happened here. Hubble's analysis of the 21st of July 2025 image showed that this was a real, physically collimated jet aimed sunward about 10 times longer than it was wide. No known solar system comet has ever produced a confirmed physical sunward jet like this. To remain so narrow while extending hundreds of thousands of kilometers, it would have to push against the outward flowing solar wind, which travels at roughly 400 to 800 kilometers per second. Loeb notes that a beam of charged particles directed sunward could, in principle, act like a shield, deflecting the solar wind from striking the nucleus. He also points out that the surrounding dust veil had exactly the column density needed to block direct sunlight from the nucleus. One structure, two useful functions. Anomaly 6 is the rotation axis alignment. Before solar heating could meaningfully reshape anything, 3I, Atlas already had its rotation axis aligned within 8 degrees of the sun-facing direction. For a random object, the odds of that are about 0.5%, or 1 inch 200. Combine that with the earlier 1 inch 500 trajectory alignment, and the running probability drops to 1 inch 100,000. Anomaly 7 pushes it further. The pre-perihelion sunward jet did not stay fixed. It wobbled back and forth with a 7-1-hour period, matching the nucleus rotation, and the wobble reached plus or minus 20 degrees. For this pattern, to keep the jet pointed sunward, the base of the jet had to sit within 8 degrees of the sun-facing pole. That is another 0.5% event independent of the axis alignment. Multiply again, and the odds become 1 inch 20 million. Then comes anomaly 8, and this is where the geometry becomes almost surreal. Before perihelion, there was a sunward jet from one pole. After perihelion, once 3I, Atlas rounded the sun and its direction changed, there was another sunward jet from the opposite pole. 2 poles, 2 separate jets, both aimed toward the sun before and after a 1/6-degree deflection in travel direction. Each by itself carries a 0.5% chance. Together, that pair gives 1 inch 40,000, and folded into the running total, the combined odds plunge into the hundreds of millions to 1. Anomaly 9 is a physical problem rather than a geometric one. The sunward jets were active only when facing the sun, but the base of the pre-perihelion jet sat on the night side before perihelion, and the base of the post-perihelion jet sat on the night side after perihelion. In a natural comet, heat spreads through the body by conduction. You should not be able to keep those night side regions thermally isolated for months while still producing this kind of behavior. Known comet physics does not offer a good mechanism for that level of insulation. Anomaly 10 makes the symmetry even tighter. At perihelion, the combined gravity of the Sun and Jupiter bent the trajectory of 3I, Atlas, by 16 degrees. The opening angle of the pre-perihelion jet was 8 degrees. 16 is exactly twice 8. That means the geometry of the wobbling jet system was preserved perfectly across perihelion. If the deflection had been 15 degrees or 17 degrees instead, the same clean before and after symmetry would not hold. The final anomaly in this section is the Earth alignment. On the 22nd of January 2026, the Sun, Earth, and 3I, Atlas lined up within 0.69 degrees. That kind of opposition surge can happen with comets. What is unusual is that, at this exact moment, the anti-tail was pointing directly at Earth. A physically sunward structure ended up aligned with Earth at the closest Earth-Sun object alignment of the entire passage. And just when that seems like enough coincidence for one object, the next anomaly connects 3I, Atlas, to one of the most famous unsolved signals in astronomical history. The 12th anomaly pulls us into one of the most famous mysteries in the history of astronomy. In 1977, the Big Ear radio telescope at Ohio State University detected a signal unlike anything ever recorded before or since. It lasted exactly 72 seconds and appeared at the hydrogen frequency of 1,420 megahertz, the exact frequency scientists had long suggested would be the logical choice for interstellar communication. When the astronomer reviewing the data saw how unusually strong and clean the signal was, he circled the numbers and wrote a single word in the margin: wow. The name stuck. Despite decades of searching, the signal has never been detected again. What makes this relevant to 3I Atlas is the direction. The WOW signal originated from the constellation Sagittarius. 3I Atlas also entered our solar system from the direction of Sagittarius. The angular separation between the two directions is about 9 degrees. For a random interstellar trajectory to arrive within 9 degrees of the WOW signal's origin, the probability is roughly 0.6%, or about 1 inch 170. A signal that has never been explained and an object that has never been explained appear from nearly the same direction in the sky, separated by 48 years. Anomaly 13 concerns the jet structure revealed after perihelion. Between November 2025 and February 2026, the Hubble Space Telescope captured 40 detailed images of 3I Atlas. When Loeb and his colleague Scarato applied a rotational gradient filter called the Larsen-Sekanina technique, which removes the bright circular glow of the coma and exposes internal structures, something surprising appeared. Instead of a single jet or randomly scattered activity, the images revealed 3 smaller jets. They were not placed randomly around the nucleus. They were spaced evenly at exactly 120 degrees from each other. Natural comet outgassing is driven by pockets of volatile ice hidden beneath the surface. Those pockets form randomly. Random placement does not normally produce a perfect geometric pattern like 3 jets separated by equal 120 degree intervals. Loeb did not claim this proved anything extraordinary, but in the published scientific paper, he raised a simple question: are these 3 jets the result of unusual but natural ice pockets, or could they represent something more structured, such as thruster-like activity? The paper leaves the question open. Anomaly 14 involves the way the object accelerates. In normal comets, gas escaping from the sunlit side produces a small rocket-like push that mostly points away from the Sunday. This behavior is described by a model developed by Brian Marsden in 1973. But measurements of 3I, Atlas, produce conflicting results. One study, using more than 7,700 astrometric observations, suggested that the sideways acceleration, perpendicular to the Sun-comet line, was about as strong as the outward push. NASA's own solution, based on a smaller but carefully vetted set of 782 observations, found the outward push to be 5 times stronger than the sideways one. Two independent teams examining the same object reached dramatically different conclusions about the direction of the force acting on it. The disagreement remains unresolved. Scientists hope the upcoming Jupiter flyby will provide new measurements that might finally clarify the motion. Anomaly 15 concerns chemistry. Before perihelion, spectroscopic analysis of the gas cloud around 3I, Atlas detected an unusual chemical ratio. The amount of nickel relative to cyanide was far higher than in any known comet, including the previous interstellar visitor 2I, Borisov. Even more puzzling, the nickel appeared with far less iron than expected. In nature, nickel and iron usually form together during stellar explosions and are found in roughly consistent ratios across cosmic objects. A nickel-rich environment with suppressed iron resembles compositions seen in some industrial alloys rather than typical cosmic chemistry. Loeb did not argue that the material must be artificial. He simply pointed out that the ratio does not match anything previously observed in natural cometary material. Anomaly 16 deepens the puzzle. The anti-tail of 3I, Atlas, stretched hundreds of thousands of kilometers through the solar wind. For dust particles to remain so tightly structured over that distance, they must be larger than the tiny grains typically found in comet tails. Larger grains resist radiation pressure and are harder to push away. But if the particles are that large, the amount of mass required to produce the brightness seen in Hubble images becomes extremely large. In other words, small particles cannot explain the structure, and large particles require an unrealistic amount of mass. There is no easy combination of particle size and mass that explains both the shape and brightness of the antitail at the same time. And just when the dust puzzle seems difficult enough, the next anomaly introduces an even stranger disappearance. The 17th anomaly involves water ice, one of the most common substances in comets. In August 2025, NASA's SPHERICS mission observed 3I Atlas before it reached perihelion. The telescope detected clear spectral signatures of crystalline water ice, including absorption features at wavelengths of 1.5 and 2 micrometers. In simple terms, the ice was definitely there. Then, something unexpected happened. When SPHERICS observed the object again in December 2025, after it had passed close to the Sun, the spectral signature of water ice had vanished. It did not weaken gradually. It disappeared. This part alone is not shocking, because ice near the surface can sublimate away when a comet approaches the Sunday. But normally, that process weakens the structure of the nucleus. With the previous interstellar comet, 2I, Borisov, pieces of the comet broke apart after perihelion as its volatile material evaporated. With 3I, Atlas, there was no fragmentation event at all. The surface ice disappeared, yet the object remained intact. Instead of breaking apart, it experienced a violent outburst in December 2025 that released methanol, methane, and cyanide from deeper layers beneath the surface. The eruption was strong enough to be classified as a major event, and yet the nucleus survived without shattering. The 18th anomaly comes from isotopes. A paper submitted to Nature on March 6 measured the ratio of deuterium to hydrogen in the water of 3I, Atlas. Deuterium is a heavier form of hydrogen that forms more easily in extremely cold environments. In most comets within our solar system, the deuterium to hydrogen ratio falls between about 0.03 and 0.06%. For 3I Atlas, the measurement was about 8.95%. That is more than 10 times higher than the value seen in our solar system and roughly 12 standard deviations above the average measured in protostars throughout the Milky Way. Such an enrichment suggests formation in a very cold environment, below about 30 Kelvin, and in a region of the galaxy that existed long before our Sun was born. Anomaly 19 involves carbon isotopes. The same study measured the ratio of carbon 1:2 to carbon 13 inches carbon monoxide and carbon dioxide molecules released from the object. Solar system comets typically show ratios between about 90 and 120. Nearby interstellar molecular clouds usually show values around 60 to 80, but the values measured for 3I Atlas ranged from roughly 123 to 191 depending on the molecule. A higher ratio means relatively less carbon, 1:3, which in turn implies that fewer generations of stars had processed the material before the object formed. In other words, it likely formed very early in the galaxy's history, perhaps 10 to 12 billion years ago. Two independent isotopic clocks, hydrogen and carbon, both point toward the same extremely ancient origin. Anomaly 20 concerns nitrogen isotopes. Another research group measured the ratio of nitrogen 1,4 to nitrogen 15 inches cyanide molecules released from the comet. Once again, the result was unusual. The ratio was more than twice the value typically measured in solar system comets. What makes this remarkable is that three separate isotopic systems, hydrogen, carbon, and nitrogen, were measured by different teams using different instruments, yet all three tell a consistent story. The material in 3I Atlas appears to have formed in a cold, metal, poor region of the early Milky Way long before the birth of our solar system. Anomaly 21 introduces another chemical mystery. Observations from the ALMA Observatory measured the production rate of methanol relative to hydrogen cyanide in the comet's gas emissions. In comets within our solar system, this ratio usually falls between about 1 and 20, with a median near 5. In 3I Atlas, the ratio ranged from about 70 to 120. Methanol was not a minor ingredient. It was a dominant component of the gas output. No comet in our solar system has ever displayed such a high methanol to HCN ratio. Chemically speaking, it looks like a completely different class of object. The final anomaly in this sequence is the persistence of formaldehyde, a molecule known as H2CO. During the James Webb Space Telescope's final dedicated observations in late January 2026, when 3I Atlas was already more than 3 astronomical units from the Sun, scientists still detected methanol and formaldehyde in the surrounding gas cloud. At that distance, solar heating is 9 times weaker than at Earth's orbit. Normally, comet activity that far out is dominated by carbon monoxide rather than complex organic molecules. Yet here, formaldehyde remained present. This molecule is important because it is considered a prebiotic compound involved in pathways that can lead to sugars and amino acid precursors. Its persistence so far from the Sun suggests either an unusually rich surface concentration or an unknown mechanism allowing organic material to escape even at very low temperatures. And with that observation, the count reaches 22 anomalies, each documented, each measured, and each raising the same quiet question about what exactly passed through our solar system. By the time we reach anomaly 22, something important becomes clear. None of these observations alone proves that 3I, Atlas, is anything extraordinary. In science, individual anomalies often fade once more data arrives, but what makes this object so unusual is not one strange feature, it is the accumulation of many independent measurements pointing in directions that do not easily fit together. So the next step is the same calculation Avi Loeb proposed in his methodology. Take the anomalies that have measurable probabilities and multiply them together. Let's start with the geometric coincidences. The second anomaly, the arrival trajectory within 5 degrees of the ecliptic plane, carries a probability of about 0.2% or 1 in 500. The sixth anomaly, the alignment of the rotation axis within 8 degrees of the sun-facing direction before heating effects could influence it, has a probability of about 0.5% or 1 in 200. The seventh anomaly, where the base of the jet must sit within 8 degrees of the sun-facing pole to produce the observed wobbling pattern, also has a probability of about 0.5%, again 1 in 200. Then we add anomaly 8, the before and after symmetry of the sunward jets at opposite poles. Each of those configurations has about a 0.5% probability. When combined, the chance of both occurring together becomes about 1 in 40,000. Finally, anomaly 12, the directional coincidence with the WOW signal region in Sagittarius, carries an estimated probability of about 0.6%, roughly 1 in 167. Now multiply them. 1 in 500 times, 1 in 200 times, another 1 in 200 times, 1 in 40,000 times, 1 in 167. The result is approximately 1 in 500 trillion. That is 500 trillion to 1 against these 5 geometric coincidences occurring together purely by chance, assuming they are independent events. This number does not include the other anomalies, the mass budget discrepancy, the strange dust-particle paradox, the thermal insulation problem, the unusual isotopic ratios, the nickel chemistry, or the 3 jets arranged at perfect 1, 2, 0 degree spacing.